Before a newborn takes its first meal, the interior of the intestinal cavity is essentially a blank biological slate, clean, smooth, and entirely uncolonized. But this state is temporary. Within hours of birth, the infant transitions from a sterile womb into an external world teeming with microbes, and these organisms immediately begin seeking a place to settle. The arrival of breast milk introduces the first set of active maternal signals. This fluid delivers the specific components needed to guide the development of the infant's gut during its most vulnerable window. This delivery is a responsive biological loop. As the baby feeds, the mother's posterior pituitary gland releases oxytocin, a hormone that triggers milk flow and continuously updates the levels of protective proteins provided to the infant. This chemical bridge allows the mother's immune system to directly coordinate the newborn's first biological defenses, helping the gut transition safely into a microbe-filled world. As the first waves of milk enter the gut, specialized maternal proteins settle onto the intestinal lining. These proteins act with high precision. They envelop friendly bacteria to colonize the tissue, while physically repelling invasive pathogens attempting to attach. These microscopic shields are primarily composed of secretory immunoglobulin A and lactoferrin. Together, they selectively filter incoming microbes, determining which organisms can stay. By blocking harmful bacteria from taking over the intestinal surface, these shields ensure the gut begins its development on a secure, stable foundation. This early screening process allows the infant's immune system to interact with its first microbes without triggering an immediate inflammatory alarm. Following the proteins, the milk delivers dense, complex sugar structures that the infant's own digestive enzymes cannot break down. These complex sugars, that known as human milk oligosaccharides, or HMOs, pass through the upper digestive tract unabsorbed. They reach the colon fully intact to serve as the primary fuel source for beneficial bacterial cells. Supported by this targeted energy supply, specialized bacteria like Bifidobacterium multiply rapidly. They quickly dominate the gut, maintaining a healthy, low-diversity environment that is appropriate for a newborn. HMOs provide a second layer of defense by acting as decoy receptors. They mimic the structures of the baby's cell walls, tricking harmful germs into binding to the sugars instead of the tissue. These trapped germs are then safely flushed out of the body. As the friendly bacteria consume these sugars, they produce short-chain fatty acids. The infant's gut wall uses these acids as fuel to increase its transepithelial electrical resistance, physically tightening the gaps between cells to create a leak-proof barrier. By coordinating the growth of a dedicated bacterial defense force while simultaneously strengthening the intestinal lining, these sugars establish a dual-layered physical and biological shield. In the absence of these specific maternal signals, the infant's gut follows a visually and biologically distinct developmental pathway. Because standard formulas lack natural HMOs and maternal antibodies, they use artificial prebiotic fibers to attempt to stimulate bacterial growth. This data visualization shows the resulting difference in the gut ecosystem. While the breastfed gut remains specialized and simple, the formula-fed gut develops a highly diverse population of complex bacteria that typically belongs in an older child. These complex bacteria can grow too quickly, entering the environment before the infant's immune system is ready to manage them. This premature expansion can trigger localized irritation and a state of bacterial imbalance known as dysbiosis. Without the adaptive feedback of mother's milk, the gut is pushed onto an alternative metabolic trajectory, requiring the infant to process nutrients and microbes using a different set of biological rules. These early microbial interactions establish the foundational structure of the intestinal tissue, which eventually matures into a permanent biological ecosystem. When the early immune maturation is delayed or altered, the body may become prone to overreactions later in life. This is why alternative developmental pathways are linked to a higher risk of conditions like atopic dermatitis and food allergies. For premature infants, these early signals are critical. The absence of specific protective sugars like DSLNT leaves their fragile intestinal lining exposed to severe, life-threatening inflammation and tissue damage. These feeding modes also interact with prenatal factors, such as maternal weight gain during pregnancy. Together, they help determine how the child will extract energy from food and manage their long-term metabolism. When the gut systems are correctly aligned, the microbes, protective proteins, and physical barriers work as a single harmonious unit, providing the infant with a resilient defense that lasts a lifetime.